Good morning. So today we will continue our discussion on PEC water splitting and hydrogen production. So what we have discussed in this module so far is that there is a need for fuel which do not pollute the environment, and hydrogen was found to be one. And hydrogen, we know that is the lightest element. Okay, if we use hydrogen as fuel, then byproducts are not at all pollutant, and also it can be stored and it can be used as a very huge source of energy. So there are two important aspects of hydrogen research. One is generation of hydrogen and another is storage of hydrogen. So in this particular module, I discussed one particular process of generation of hydrogen, which is also known as green production of hydrogen or production of green hydrogen. Okay, and that is what is PEC water splitting. And we have also seen that what is the process involved in the PEC water splitting. Broadly, it is actually splitting of water with the help of sunlight. Okay, and there is no byproduct which contain any kind of pollutant element. So therefore, it's a completely green production process. And then we have seen that what are the materials one should choose in order to make an efficient way of water splitting, and what are the essential property and also band gap that is required in order to split water efficiently and produce hydrogen. And then we also discussed about when we introduce different nanomaterial, how they improve the efficiency of hydrogen production by this method. Okay, and then we have of course seen how to generate photovoltaic, what is the physics behind it, okay, and this overall application of this particular process. So now in this lecture we will review this module again with different question as we had done for all other module previously. So let us look at few questions. So first is, what are different process to generate hydrogen? So I have already discussed that there are several ways that one can generate hydrogen. So if you look at the process broadly, the hydrogen production can broadly categorized as electrochemical method, thermochemical method, and biological method. Now when we talk about electrochemical method, we have two process, electrolysis and photoelectrolysis. So electrolysis is a process which all of us know that how it works. Electrolysis is that when we have an electrolyzer, we have two electrodes, cathode and anode. We give electrical energy to the system, and then there is a charge movement in the electrolyzer. Okay. Eventually, if this water is there in the electrolyzer, it is converted to hydrogen and oxygen. But we have to apply very high voltage in order to get hydrogen and oxygen, or say hydrogen, by this process. Now photoelectrolysis is a process which actually is the subject of this module, which I have discussed, and reviewing the questions. Here we do not give this high voltage or electric supply. What is done with the help of sunlight? The water is splitted. Here system is same. We have one cathode, one anode, and in between there is electrolyzer, okay, which contains water. And then when sunlight falls, the cathode and anode in such a way, or the electrode, the sunlight when it falls to a, suppose in anode which is photoanode, and then it gives an electrical energy. So electrical energy gets generated from the solar energy, and it gives energy to the electrolyzer and split it in hydrogen and oxygen, and eventually the green hydrogen production takes place. So now what are the other methods that those people use? And now also there are large number of production of hydrogen is taking place using these methods. So one is a partial oxidation, which falls in the thermochemical method. In partial oxidation, what happened that you take a hydrocarbon, okay, say methane or any other hydrocarbon, and take it to a high temperature, okay, maybe 700, 800 degrees centigrade, and with limited oxygen flow, this hydrocarbon is burned, and then hydrogen, carbon dioxide, etc. are produced. Okay. So this is partial oxidation method, which typically one can do in a furnace. And then coal gasification. In this case, what we do, or people do in the coal gasification method, it is again a high temperature process. Okay. So coal is actually burnt at very high temperature, okay, in the presence of steam or air, and then the hydrogen along with other gases like carbon dioxide, carbon monoxide, etc. are produced, and one can store hydrogen after the generation. And also one can have something like biomass gasification, which almost similar process, where one can use the organic material and burn it in the presence of oxygen or steam, and then produce hydrogen. Steam reforming is also almost similar process, where the hydrocarbon, okay, or in a natural gas, it is in the presence of steam, it is burned at high temperature, eventually producing hydrogen and other gases like carbon dioxide, carbon monoxide, or other gases which the hydrocarbon contains, the elements. And then one can have this third method, which is biological method like fermentation, where microorganisms like bacteria can do this job. Any organic material can be fermented using this bacteria, and the hydrogen can be produced. Okay. And photosynthesis is also a biological process. It happens in plant, where sunlight falls and there is chlorophyll which absorbs sunlight, and then it produces the glucose, so sugar from carbon dioxide, and it also produces oxygen from water. Okay. So these are all steps or the methods or the process which people see either in nature or industry or in the laboratory, how regularly the people are producing hydrogen. All methods are not green process. Photoelectrolysis is a green process. There is one technique which is coming up recently, that is called nuclear hydrogen production, where nuclear energy is used combining with some electrolyzer to produce green hydrogen. So, let me see the second question. What is the basic difference between photosynthesis, photoelectrolysis and photovoltaics? This is a very important process because you know the photosynthesis is a process which happens in nature, in the plant, and photoelectrolysis and photovoltaics is something which is happening in the laboratory or artificially people are doing. So, if I look at say photosynthesis process first, photosynthesis process, it is actually sunlight falling. So, I can say the photon falling on plant and carbon dioxide gets converted to sugar. Okay. It is actually the leaf which is the engine of this particular fuel generation. Oxygen and hydrogen is produced from water. Okay. So, the energy input comes from the sun, okay, or sunlight. So, now I go to photovoltaic process which we have already discussed. In photovoltaic process, it is basically we have a semiconductor and say metal junction, sunlight falls here, okay, and what we get as an output is electrical energy or the voltage. All right. And then in this photoelectrolysis, which is the third process, we have again a semiconductor, a metal, and in between we have electrolyzer, sunlight fall in this system, and this also contains H2O, which get split to H2 plus O2. Okay. So, broadly if we look at this process, all these three processes are driven by sunlight, that is the energy which comes the photons of sunlight which carries the energy, and then it helps in triggering this particular process doing different jobs. So, if we look at this broadly, that it is basically conversion of solar energy or the light energy to either as fuel, okay, biological fuel like sugar, it is a food, so we can tell it is a fuel in the plant, or it gets converted into electrical energy. Okay. So, these three processes actually combine these particular aspects, the generation of fuel and electrical energy, production of hydrogen, oxygen, etc., by these three processes. Okay. So, we go to the next question. What are the essential requirements for of PEC water splitting process? So, what we have seen that in order to have a PEC water splitting process, what is the importance that because sunlight falls on the PEC water splitting setup, which actually consists of one anode, photoanode, and a cathode, okay, or we say it is a counter electrode. So therefore, there has to be some kind of condition which is required in order to produce hydrogen or in order to split water and to produce hydrogen and oxygen. So what we have discussed is that if I write the condition 1, okay, the photo response, whatever material we are using as anode, the photo response should be good enough. We can write it as photo response should be good enough for, say, particularly visible region of light. So this is the first condition, and there should be a strong absorption of light, which actually it follows this first condition, and strong absorption of light. Okay, so once light get absorbed in the photoanode, then the charge carriers are generated, electron and hole. Okay, so there should be an efficient generation of charge carrier, which is the third essential condition. Of electron hole pairs. Okay, and then once these carriers are produced, they should not recombine. Okay, so therefore there should be a minimum recombination, or recombination should be suppressed. Low recombination rate. This is the fourth condition. Okay, and what is the fifth condition? Fifth condition is that charges should have sufficient energy so that it can split water. Okay, charge carriers should have enough energy to split H2O. So for entire this PC water splitting process, these 5 conditions are extremely important. Okay, so tomorrow if you start some research on this and you want to look at a material which can be used for for the photoanode or the electrodes, okay, then one has to look at all these important points, that how good it satisfies, or your entire PC water splitting setup which you design and fabricate for hydrogen production, is whether these 5 conditions are essential conditions are critically met or not. Okay, so we go to the next question. What are the 2 important functions of the PC water splitting process? What are essential steps of this process? If we look at broadly this PC water splitting process, actually there are 2 functions. Okay, one function is, you can say, optical function. What is optical function? Optical function is a process where sunlight is falling on the electrode and it is getting absorbed by the electrode. Okay, so this is called optical function. And the second one is catalytic function catalytic function. So, what is catalytic function? Catalytic function is that when sunlight is absorbed in the photoelectrode, then all the steps. So, what the steps are happening here? The steps are what we know that it is excitation of electron hole pair in the photoelectrode. Second step is charge separation in the photoelectrode. Okay. Third is charge transfer within PEC, that means charge movement in the electrolyzer or inside the cell, and then generation of PEC voltage and splitting of water. Basically, it splits like this, which actually add 2 electron and make hydrogen. Or produce hydrogen or green hydrogen. Okay. So, this is all about this process and the steps of PEC water splitting, and the two important function as I mentioned, that optical function as well as the catalytic function. In a N-type semiconductor, electrolyte metal based water splitting process show the oxidation and reduction indicating generation of H2. Okay. So, we know that H2O splitting and production of H2 and oxygen are basically a hydrogen evolution reaction and an oxygen evolution reaction. So, I discussed earlier that there are two reactions which is happening here. One is HER, that is hydrogen evolution reaction, and OER, that is oxygen evolution reaction. Okay. So, let us see that when we have a system where we have an N-type semiconductor as an electrode and a metal as another electrode. Okay. So, this is a N-type semiconductor. So, N-type semiconductor, I write it in this manner. We have a conduction band, valence band. Okay. And then there is a Fermi level here. All right. And then light is falling, and then we have a metal electrode. Okay. So, what is happening that here we have, as soon as light falls, we have the generation of hole and electron. All right. So, this hole, so this is electrolyzer which contains water, this whole actually reacts with water, okay, and it gives plus. There is a reaction which take place here, and this H plus actually it goes here, all right, and the electron it starts journey here, comes to here, and this H plus which is going here actually gets electron. So, the reaction which takes place here is 2H plus plus okay. So, we have these two reactions now. One you can say OER, okay, oxygen evolution reaction, and another is HER, that is hydrogen evolution reaction. Okay. We can change these electrodes as I have discussed. We can have this N-type electrode, P-type electrode, or P-type electrode and metal electrode. So, depending upon which electrode we are selecting as photoanode and counter electrode, the HER and OER reaction changes, or it takes place at different location. Show the energy levels in a redox electrolyte system. Okay. So, what is the redox energy? So, what we have discussed that this electrolyte suppose this is energy, okay. We can consider one density of state, which is empty as the density of state of oxidation, another density of state which is a field or density of state for reduction, okay, and then we have an energy level here which is E redox. Okay. So, this is a way we describe the energy levels of an electrolyte, and we have also seen that when this electrolyte is comes in contact with the semiconductor, now we have conduction band, valence band of semiconductor, how these energies get aligned with the energy levels of semiconductor or energy bands of semiconductor, and then the photovoltage is generated. Let us go to the next question. For an efficient PEC water splitting, what are the position of CBM and VBM with respect to redox potential, that is conduction band minima and valence band maxima with respect to redox potential. So, let me just note down or tell you again the issues which are important for PEC water splitting. So, number one is the semiconductor, okay, the system which is used in the PEC water splitting setup must generate sufficient voltage upon irradiation to split water. This is a very important point. Okay. Second point, the band gap issue. So, what should be the bulk band gap? The bulk band gap, okay, must be the small enough to absorb significant portion of the solar spectrum. Why small enough? because the the energy for the redox reaction is 1.23 electron volt. That is what we have studied, and therefore the band gap should not be very high. Okay. So, although TiO2 was used as photoanode initially because of its stability, and then people started looking at other material because the TiO2 band gap is quite high. Now, the third point comes, that is the band edge potential at the surface must straddle the hydrogen and oxygen redox potential. This is where the first question is. The answer to the first question is, so what does it mean? It means that if we decide two line, one is for HER, okay, or I can write it here. OER and HER, which is say 1.23 electron volt. Then we have to place this material, the conduction band minima and valence band maxima. The ideal situation is okay. There could be some situation where conduction band maxima may be higher and valence band maxima is top of that HER, or vice versa, VBM may be here and CBM may be very close to this line. Okay. So, this is a third important point which one is to look at for PC water splitting. And the fourth issue is this system, whatever the entire system, whatever we are considering for PC water splitting, should have long term stability. That is important against any type of corrosion which is happening in this aqueous electrolyte solution. So, it should be corrosion free. And the fifth is very important point, the charge transfer from the surface of the semiconductor to the solution must be facile to minimize energy losses. Energy loss should be minimized due to kinetic overpotential, okay, because the overpotential is generated, which we have discussed, okay, and selective for the hydrogen evolution reaction and oxygen evolution reaction. This is very important point and which is essential when we design a PEC water splitting setup. So, you know that in this in the PEC water splitting setup, typically we have two electrodes, okay, and then there is a reference electrode with respect to which we measure the voltage and current, and we have to check the overpotential, okay, for the measurement. Now, we go to the next question. What is the PEC water splitting equation given by Fujishima and Honda? This is the first paper in 1972, which was published in Nature by Fujishima and Honda. Okay. So, what if we look at this equation, because as I told you, the TiO2 was used as photoanode. So, when it reacts with photon, okay, it gives 2 electrons in 2 holes. So, that is actually the first step, that is excitation of TiO2 by photon or light. Second step is that these holes, they react with H2O, producing oxygen and H plus, which happens at the TiO2 anode, okay. And then this electron which are produced here, they interact with this H plus ions and produces hydrogen where at the platinum cathode. So, just now I have shown you schematically how it is happening when we have an n-type semiconductor and a counter electrode which is a metal, say platinum. Okay. So, overall if you write this equation, the overall equation is H2O interacting with photon producing oxygen and hydrogen. Okay, this is what was proposed by Fujishima and Honda in their first paper, and as I mentioned in the lecture that after that there is a huge citation of this paper because people realize that it is a very the important process of generation of green hydrogen. But now what are the issues with TiO2 as photoanode? The main issue is again the energy band gap because TiO2 energy band gap is quite high, say 3.4 electron volt. Okay. So, what happens? Lot of light gets transmitted through the TiO2. Although because of the stability issue, they have used TiO2 and people knew that time how to use TiO2 in the electrolysis process. Okay. But it there are a lot of photons which actually is lost because of the transmission. Okay. So, therefore, the efficiency of hydrogen production is not very good. All right. And another issue with TiO2 was that the charge diffusion length is also not very good in TiO2. So, these are the two important issues, and then people started thinking that whether they should modify TiO2, okay, or use another material as photoanode. So, one's thought is that if one can modify TiO2. So, one of the modification which people can do by doping it with some element, and people started doping it with carbon. Okay. So, what happened when the carbon is doped, there is interband states formation which I discussed, and because of that the absorption edge shifts, okay, towards higher wavelength side. Okay, and therefore, the more and more visible light can be absorbed when TiO2 is doped with carbon. Okay, and this is what was demonstrated in this work, which you can see that carbon there is different atomic percent, 0% to 2%, and then there is a clear enhancement. Say you consider this one which is 0% and this one which is 2%, and if you look at the photocurrent, it is actually significantly enhanced, and the significant enhancement, photocurrent enhancement, due to enhanced absorption of light. Still the research is going on, people are trying to find the elements and doping in TiO2 and enhance the absorption and enhancing the photocurrent. Okay. But another work which people do, which I will discuss, that just by changing the structure of TiO2 itself or the morphology of TiO2 itself, that means if you can go to the nanomorphology, suppose I use the nanorod of TiO2, then whether we can have a improvement in the efficiency. We will see that. So, now I review this chapter with few frequently asked question. So, the first question is, what are the basic differences between PEC and PV? So, I already discussed that the basic difference between PEC and PV is that in photovoltaics we have a semiconductor junction I mean semiconductor based photovoltaics or junction photovoltaics. And then we have a semiconductor to metal interface, and when light falls on the semiconductor junction, it produces charge carriers which move towards the semiconductor metal interface and flows outside the circuit, eventually generating voltage. That is photovoltaic effect. In PEC water splitting process, the sunlight falls. Again, here we have a semiconductor and metal or semiconductor. Okay, in between there is an electrolyzer which contains H2O, and the energy which is absorbed in the photoanode, which suppose is a semiconductor, this energy gets converted to electrolyzer in order to split H2O, okay, and this energy is carried by the charge carriers which are generated in the semiconductor, and the hydrogen production takes place. Okay. So, one process, that is photovoltaics, is actually conversion of sunlight to electrical energy. Here the conversion of light to, of course we generate voltage and current, but the importance is that we generate H2, which is a kind of fuel which can be used later after it is stored and collected. Okay. So, now the second question is, show PEC water splitting reaction on a reaction surface. Okay. So, for PEC water splitting, what should be the suitable band gap for PEC water splitting? Why? So, first let us see the first question. So, if we look at the reaction surface, okay, photons falling here, it is producing electron, and hole moves here, electron moves here in another side of the surface. Okay. So, here all right. So, here the first one is the absorption of photon. I can mark it as first one, absorption of photon. Okay. The second one is generation of pair. Third one is the migration. One should also write third one here, the suppression of recombination. Okay. So, these are the fourth one, this is fourth, this is fourth. Once the charges are migrated, migration of electron and hole to the reaction surface, and triggering the reaction, the HER and OE. Okay, so this is a complete process of PEC water splitting and making hydrogen and oxygen on the reaction surface. Fine. So let us look at the third question. Show schematically oxygen and hydrogen evolution when N-type or P-type material is used as photoanode and we have metal as counter electrode. So if you look at this, say N-type, this is a valence band and conduction band. I have already discussed this. Here what happened, this electron, this is a band bending when it is in the electrolyte and the electron moves in this path which is generated here by photo excitation. Okay. And then here holes react with H2O producing O2 and H plus moves to this side which eventually produces hydrogen after taking electron from here. Okay, now if we change this photoanode by P type, here actually the light falls and electron, this is a band bending here. So, electron moves in this direction and holes we can consider that as if it is moving in this direction and therefore, now the conversion of H2O to O2 takes place here in the counter electrode and the conversion of the water to H2, this is hydrogen evolution takes place in the photoanode. So, it is exactly opposite. So, energy level wise if we again look at this process, so this is what the HER and this is OER process. So, the photon falls here, electron hole pairs are generated. Okay. So, this is conversion of or the H plus ion picking up the electrons and making H2 and here H2O reacting with hole and producing O2. Okay. So, this is reaction here and this is the reaction in the other electrode. Okay. Fine. So, let us look at the next question. NTiO2 is one of the first choice of electrode material. Why a bulk TiO2 is not a suitable material for PEC water splitting? So, I told you that the bulk TiO2 is a problem with the band gap. Although N-type TiO2 is very good because you know that it is very stable in the electrolyzer, but the bulk TiO2 is not good because of its very high band gap. Okay. And also the diffusion length of electron is not good and therefore, one need to engineer this TiO2 either by doping or going to nano dimension or different making some different structure on the nano dimensional TiO2 and we will see one particular in this question set. Now, the next question is when electrode electrolyte interface is exposed to light, a photovoltaic is generated. Why? So, we can again understand it on the basis of the energy level diagram. So, what we have discussed is that the semiconductor with valence band, Fermi level and conduction band. Okay. And then we have an electrolyte with E redox. Okay. So, there is a mismatch between these two and when they come in contact, there is a band bending in semiconductor side and now we have a common energy level. Okay. This is electrolyte. All right. So now we have a common energy level, maybe F1, right? Okay. Of the semiconductor as well as electrolyte. And in this situation, when sunlight is produced, is sunlight falls or it is photon strikes this particular junction, then there is a shift in the Fermi level. There is a shift in the Fermi level with respect to this level, and this is a voltage which is known as photovoltage. Let us write it as photovoltage. Clear? So, this is a way one can represent photovoltage, and if we put more light, if more light is absorbed in the semiconductor, then the photovoltage will, the energy line will go up and the more photovoltage will be generated. Fine. So, the last question, the two morphologies of TiO2 used for photoanode are shown in figure below. Comment on these morphologies, what role they play to improve the property as photoanode. So, I told you that the TiO2 has this problem essentially because of its very high band gap, okay, and therefore light absorption capability is not good. So, one way, as I mentioned, on that one can dope it with carbon, and then there was a clear enhancement in the photocurrent. And another way is by making nanostructure. Okay, so one work which shows that one can have a nanorod kind of TiO2 instead of a bulk TiO2. Okay, so what advantage we get in nanorod? Because there are two issues. One is, the charge carrier transport is one point in TiO2. So, if we make a nano rod, then we have a long charge carrier transport, and also as it is nanostructured morphology, there is an enhancement in surface to volume which eventually absorb more light because of geometry. Okay. And one can also make more design on this nanorod. That is what is happening here. So, this is a nanorod morphology, and this is a branched nanorod, because if I have a nanorod and then I can make branches on the nanorod. So, what are the advantages one get? Okay. So, this is nanorod morphology, and this is branched nanorod BNR. Okay. Morphology. So, I have more surface available now for photon absorption. So, one can have further enhancement of photon because of this branching, as well as one can have a very efficient transport, okay, as compared bulk TiO2. And therefore, what it has been demonstrated by these authors is that when we make look at the absorption as well as the performance of the PEC cell made up of TiO2, nanorod TiO2 and branched nanorod TiO2, we see the maximum the efficiency in branched nanorod TiO2. And also in additionally what they did, they also put some quantum dot on the branched nanorod. So, it is a proper nanoscale designing of the material, and what they have seen that with inclusion of quantum dot, there is further enhancement in the absorption and further enhancement in the photocurrent. Okay, so the designing of photoanodes at nanoscale is a very important area of research, and people are working in the laboratories. Okay. And I mentioned in my lectures several examples which we have given as how to do a nanoscale design of photoanode and to make an improved or efficient PEC water splitting system. Thank you.